and I will introduce you, okay? Okay, excellent. So the stream is already live, and so let's begin. First of all, I want to welcome everyone to our last conference of the day. I want to introduce our speaker for the evening, David Wrightson. He's an executive director of the LIGO laboratory at Caltech and professor of physics at the University of Florida. He obtained his PhD from the University of Texas at Austin in 1990 and was a researcher at Bell Communications Research and Lawrence Livermore National Laboratory before joining the University of Florida School of Physics in 1993. He has worked in numerous areas of gravitational wave detector development and gravitational wave science over the past 20 years. Between 2007 and 2011, he served as a spokesperson for the LIGO Scientific Collaboration and is an elected member of the American Physical Society and the Optical Society of the United States. So without further ado, David Wrightson.
Thank you very much for that nice introduction. And thank you for the invitation to speak with you. So I want to talk about an exciting new field, gravitational waves. And it really is, I hope to convey in this presentation, that it really is a revolution in the way we actually study the universe. And I want to start by actually showing you a movie. This is a movie that actually started the revolution. It's a simulation of an event that took place approximately 1.3 billion years ago. And those two objects that you see in the center are black holes. I think most people know what black holes are. They are basically the end stage of life of stars, where gravity overcomes every other force, and the masses collapse upon them. The mass collapses upon himself to form a singularity in space-time. And what you see around those black holes are the stars, are basically the warping of space-time due to the fact that there are enormous gravitational fields produced at the surfaces of these black holes. So these particular black holes are kind of special. The first black hole, we'll call it that black hole number 1, was 36 times more massive than the sun. The second black hole was about 30 times more massive than the sun. And these are because gravity is such an immense force that it packs all of that mass in the form of space-time curvature into a very, very small volume. In this case, the bigger black hole is 210 kilometers. The smaller black hole is 170 kilometers. So what I'm going to do is I'm going to show you a simulation of these two black holes, which are locked in orbit around one another. And well, as the movie goes, you'll see what happens. So let me just play the movie. So you can see them dancing around one another. And as they dance around, you might notice that they're getting closer and closer together. You certainly notice that the star fields behind them are really quite dramatically moving around. But I want you to concentrate on the black holes, and you can see they are getting closer together now, and eventually they're going to get together and merge and produce a big black hole. And that merger of those two black holes produced a final black hole that was about 62 solar masses, and in the instant that they merged, you may have seen a little ripple in the movie towards the end. That was a gravitational wave being emitted from this collision of these two black holes, which basically contain the energy equivalent to 3 solar masses. And because this was a very fast event, the movie that I showed you was simulated 100 times faster than reality. This was one of the brightest events in the universe. And I put bright in quotation marks on the slide because gravitational waves are not like light in some ways. They are like light in other ways, but more energy was released in a short burst of time than any other event in the universe at that particular time, and including all of the stars that are in the universe. So this was really a remarkable and truly revolutionary event. So the revolution started 1.3 billion years ago. It took 1.3 billion years for the signal to travel to Earth, where it was detected by LIGO on September 14th. So that's to frame the talk. So what I what I'm going to go into more detail now is a little bit more about gravitational waves, what they are, why we want to study them. I'll then talk about how we actually study them. What kinds of detectors do we build to detect these gravitational waves, and then talk a lot about some of the discoveries that we've made in the past 5 years, and a little bit, very little bit at the end about what we would call future horizons. So, and I hope people come away with a sense of two things. One, that this is really a new kind of astronomy that we're doing with gravitational waves, and two, that there's an immense amount of information that we've already gained in the past 5 years. So I'm going to start by talking about gravity, because at the heart of gravitational waves is gravity. And I need to educate you a little bit with general relativity. So this is going to be a very short course in general relativity, non-mathematical. So let's start with two objects, the sun and the earth. All right. How are they attracted to one another? Well, Isaac Newton in the 16th century, or the late 17th century, really thought about this problem and taught us how these objects interact with one another. So he realized that if you have two massive objects, in this case the Earth and the Sun, there's an attractive force, and it's proportional to the mass of the Sun, and proportional to the mass of the Earth. He also was able to determine that the force of attraction is proportional to the inverse of the square of the distance between the mass and the Earth. So you can write down a mathematical formula based on those two statements, and that's expressed in Newton's law of gravity, which basically says that the force between two massive objects, in this case the Sun and the Earth, is equal to a constant. We now call that constant big G. It's Newton's gravitational constant, times the mass of the Sun and the mass of the Earth over the distance squared. So R is the distance between the mass and the Earth. There's a problem with this theory, and Newton himself realized it. It's that how do these masses communicate when they're so far away from one another? In fact, gravity is a long-range force. If you have two objects that are light years apart, gigalight years apart, they still have an attraction. And it took about another 300 years before Einstein really was able to tackle this problem. And Einstein came up with a unique and very complicated and difficult to understand theory of gravity, basically based on geometry. So in Einstein's picture of the world, these two objects are there, but they sit in space. In fact, they sit in space-time, because space and time are actually related to one another through the special theory of relativity. And the interactions come not from the fact that the masses communicate directly with each other, but they warp the space-time. So if you think about that green grid, all right, if you look far away from where the masses are, so in the bottom left-hand corner, or maybe in the upper right-hand corner where things are getting darker, the grids look nice and square, or look rectangles, much like a Cartesian coordinate system. But as you get nearer to the masses, you start to see that the curvature changes. And in fact, that's what Einstein's theory tells us, that when you put massive objects in space, it warps the geometry. And that geometry is what actually communicates the instantiation of one mass with respect to another. So a sort of a simple way to say this is that space tells matter how to move, and matter tells space how to curve. So space-time curvature and matter and energy are equivalent to one another. And this is the this is the equation that Einstein came up with. It's a very complicated equation, very mathematical. In fact, it's actually a series of nonlinear differential equations, not so easy to solve. In fact, we have to use computers to solve them in most situations. But what's important about this is, and this is why gravitational wave physics and astronomy is so rich but so challenging, is that the interactions between space-time and matter and energy are very, very tiny. In other words, the coupling is very, very small. You can think of this as a spring, if you will, that space is a spring that matter can push and pull. And that coupling constant, the spring constant, if you will, is about 10 to the minus 43. So this means effectively it takes a huge amount of mass to make a little bit of a change in the geometry of space-time. So, all right. And by the way, if the mass gets too big, so pretend the sun is much, much more massive than it actually is, what will happen is all the matter would collapse on itself and it would form a black hole. All right, so what are gravitational waves? Well, gravitational waves naturally come out of the theory of general relativity. In fact, they come out if you make a few assumptions, and they're actually, the mathematics is a little bit simpler. But effectively what they are, I'm going to again do another simulation, and these are two black holes. You know, this is a cartoon. These are two black holes that are spinning around one another. And you can see that the geometry, the Cartesian system is rippling and vibrating, and then they collide, and there's a burst of geometry that goes out, and then they're left behind. So that's in fact a nice sort of conceptual way to see what gravitational waves is. We call them ripples in space-time, but they're produced actually, and this is an important part, by objects that are moving. In fact, specifically by objects that are accelerating. As two masses accelerate around one another or move around one another, they are accelerating. Right. So, but if you're a physicist and you want to actually measure a gravitational wave, you have to think about it a little more deeply. And it turns out that gravitational waves, when you write the equations down, they fall out. The amplitude of the gravitational wave is something called a strain. If anybody's had an engineering course, mechanical engineering course, or even a basic physics course, you know what a strain is. It's a change in length per unit length. The theory tells us that there are two polarizations, so sort of two flavors of gravitational waves, and a strain is a change in length per unit length. So I'm going to do a little animation here. You can see what, as a gravitational wave is passing, what it's doing. So pretend this presentation, there's a gravitational wave coming at you. So in these two polarizations, what happens is one axis stretches while the other axis compresses, and then that cycle repeats itself with the other axis stretching and one axis compressing. But to measure a gravitational wave, you want to be as far apart from the other object as possible. So you can see that here. If I measure very close to the coordinate system, there's not a lot of change in the length. All right, and that's what we're trying to measure. But if I do it out here, all right, you see it moves much further. So we want to basically, to measure a gravitational wave, a strain, we want to measure a delta L, that's a displacement, all right? And this displacement is caused by the stretching or compression of space-time. And then we want to do it over a long baseline. And that baseline is the L in the denominator of that equation. Okay, so it is interesting to note, because of Einstein's thinking about gravitational waves, because the coupling between matter and space is so small, Einstein, when he predicted gravitational waves, he thought they could never be detected. And this was in 1916. And it took about 100 years for us to detect them. And the reason Einstein thought they could never be detected was because of that coupling. But people realized that if you had the right technology, maybe it wouldn't be as hard to detect those gravitational waves. And there's a real good reason for studying them. So if you think about what we know about the universe, we know about the universe because we have optical telescopes or X-ray telescopes or radio telescopes, which detect electromagnetic waves or photons. We know about the universe because we've, in the last 50 years, built detectors that detect neutrinos, which are basically massless, almost massless particles that are produced in nuclear processes. And we also know about the universe because we build these large, massive accelerators. This one is in Switzerland, called the Large Hadron Collider, and we collide particles together and we look at what happens in those collisions. Well, gravitational waves are completely different from all of those types of observations. So they're produced by the most violent astrophysical events in the universe. The movie that I showed you was one such event. They travel unimpeded through matter. So gravitational waves are, because they couple so weakly to matter, they're very hard to detect. In fact, you're being bathed by gravitational waves right now. But perhaps the most important thing that we want to focus on is that they carry information that you can't get any other way. They carry information about the relativistic motion of bulk matter. All right. So the thing we want to do in studying and making gravitational wave detectors is realize that we're looking for really massive objects moving at relativistic speeds. And we're going to be looking out in the universe. You can't do a lab experiment to produce a gravitational wave. All right. So what do we look for? So this is just a sampling of the kinds of different events that sources, if you will, that you would see. So you've already seen the black holes colliding with the black holes. I could make a neutron star, which is a different thing. I'll say more about it later. Neutron stars are basically the products of supernova. They're very compact. They're made up of solid atomic nuclear matter, mostly neutrons. You could have neutron stars colliding with black holes. You can have neutron stars colliding with neutron stars. And those events are very transient. In other words, you saw in the movie, it started and then it stopped. There are other kinds of transient events, which we understand a little bit less about. So in addition to colliding black holes and neutron stars, supernova. If you have something called an asymmetric core collapse supernova, where the supernova, the star is spinning, and as it's spinning, it's collapsing, that could produce a gravitational wave. There are exotic objects called cosmic strings that we have yet to detect that could produce gravitational waves. They're more hard to detect because we don't really understand how to calculate what the gravitational wave looks like as we do for the coalescing binary systems. Then there are sources that are longer lived, continuous sources. Any neutron star that is spinning and has some deformations on its surface or some wobble in its spin will produce a gravitational wave, as will the Big Bang itself. At the beginning of the universe, in the first 10 to the -10 or 10 to the -20 seconds, copious quantities of gravitational waves were produced. Those are very hard to detect. So we've been able to detect the coalescing binary systems. The other three events here or sources are much harder to detect. And I should point out that whenever you build a new detector and you look for something in a new realm, in a new sector, you might actually detect something that you didn't anticipate, that you couldn't come up with a theory for, you didn't speculate would exist, and that's maybe the most exciting part of this, that we might see sources that we could never even imagine. So that's sort of a framework. General relativity produces black holes. It also produces gravitational waves, and so hopefully you got a little bit of a sense of what they are. One point that I wanted to make, and I'll make it again, is that they're very hard to detect. So let me tell you then how you would think about trying to detect them. All right, and the project that I work with is called LIGO, which is the Laser Interferometer Gravitational Wave Observatory. And at the heart of it, it uses lasers and optics to measure the time that light takes to travel from one point to another, all right, and back. And by using that as sort of a ruler, that's how we can detect gravitational waves. All right, so what's interferometry? People might know what interferometry is, but for those of you who don't, here's a sort of an introduction. You start with a laser. The laser, I'm going to run another movie here for you in a minute. The laser produces a monochromatic beam of light, which then goes to something called a beam splitter, which splits the light in two directions. Well, one direction, it allows one beam to pass straight through. I'm going to call that the x-axis. The light then goes to the x end mirror and comes back. The beam splitter is angled such that it sends half the light, and exactly half the light, to the y end mirror, all right, which is 90 degrees from that. So you can think of it as sort of a coordinate system here with the x and y axes. And then the light's going to come back and it's going to recombine, and I'll show you what happens in the movie here. And what we detect the light on a photodetector. So we're going to start. So there's the laser light. It's sort of produced as ribbons here. It's not really a beam in this simulation. The light goes out, bounces off the mirror, and then it recombines with the other light, and the arms are color coded. So the X arm is yellow and the Y arm is blue. And right now, we've positioned the mirrors such that there's no interference, but as the gravitational wave passes, in other words, as the Y arm stretches and the X arm compresses, that changes the interference pattern. And what you see is that the interference pattern on the photodiode goes from bright to dark, back to bright, back to dark. So what really is happening here is the passing gravitational wave is changing the time of light travel along the two arms in a different way, such that it changes the interference as a function of time when they get back to the beam splitter, so that you can then record that on that photodiode there. It's a screen in the simulation. Now, this exaggerated greatly the amount of shifting. In the movie, the shift was about 1 wavelength. In fact, the shift is about 10 to the minus 12 fraction of a wavelength. So it's a very, very tiny shift of one arm relative to the other. All right. So that's simple interferometry. This is more complex interferometry. This is what LIGO is. LIGO is 2 detectors, one in Livingston, Louisiana, in the southeastern part of the United States, one in Hanford, Washington, in the northwestern part of the United States. They're about 3,000 kilometers apart. And the laser, hopefully, I don't know if you can see my cursor here. Hopefully you can. The laser in the simulation is actually going to be right here. The beam splitter is going to be right here. And the end mirrors, this would be the Y end mirror here, and the X end mirror is sort of off to the right here. So you can see that this is basically the same kind of interferometer I showed you, just much, much bigger. And for a sense of scale, those are cars. That's a parking lot. So you get a sense of how big these are. Here's the Hanford Interferometer. It's exactly the same as the Livingston Interferometer. It's just in another part of the United States. And now here's the key, all right? That remember, gravitational wave amplitudes are strains. That's the change in length per unit length. So we're trying to measure a displacement over a baseline. And in our case, the baseline, the distance between the 2 points we're trying to measure is 4 kilometers, all right? So 4 kilometers to measure gravitational waves that are produced from colliding black holes, it requires measuring displacements to the level of about 10 to the minus 18 meters. All right, so how big, or rather how small, is 10 to the minus 18 meters? Well, just as a sense of comparison, if you take the diameter of a hydrogen atom, which is a proton with an electron, orbiting around it, that's about 10 to the minus 10 meters. All right, so this is 8 orders of magnitude smaller. It's actually even smaller than the diameter of a proton by about 3 orders of magnitude. So these are incredibly challenging measurements, because you're trying to measure a tiny displacement, a delta L of 10 to the minus 18 meters over a distance of 4 kilometers. All right, but you're doing it over the Earth, and so you have on the Earth, on top of the Earth. So you have to figure out a way to make sure that none of the other influences that the Earth can exert on these interferometer components will shake the mirrors any more than that. Because if they do, then we're not detecting gravitational waves anymore. We're detecting something else. So the interferometer is actually more complicated. And this is the next level of complication up. The picture on the left-hand side shows you can see, of course, the laser here. You can see the beam splitter here. You can see the end test masses here. This would be the X end and the Y end. And you see a lot of other optics. All right, you see a power recycling mirror, a signal recycling mirror. So you see a lot of other cavities here. So these other optical elements are put into the interferometer to effectively enhance its sensitivity. One way of saying it is that we actually enhance the storage time of the light in the interferometer. Another way of saying it is that we enhance the amount of phase shift that one gets, the gain in the phase shift as a function of displacement. Either way of thinking about it is correct. You can write down mathematical equations that actually show you how that happens. But the important point here is that you have to keep all of these optics and mirrors quite quiet, and you have to start with a very good laser. So that picture on the right is our laser. This is a 200-watt stabilized neodymium YAG laser. It's one of the world's most stable laser, and as you can tell by the people who are in the picture, it's an ultra clean environment because these laser powers are so high that if the laser beam hits a speck of dust, which is on a mirror or something like that, it can actually damage the mirror. So we have to take great care to be very, very clean in a clean environment here. So that starts with the laser. Actually, at the real heart of LIGO, at these interferometers, is the seismic isolation system. So we want to keep the mirrors from actually being vibrated by the ground. The ground is moving. It's moving much, much more than the displacements that we are trying to detect. So we use something called active seismic isolation. A good example or a sort of analogy of it is if you have a car, say a nice Mercedes-Benz or something like that, it has active stabilization control of the driving. As you go across bumpy roads, the car senses the bumps and evens out the car so that the passengers and the driver don't feel the bumps. We do the same kind of thing. We use basically active feedback. We have seismometers that read the ground motion out and then feed it back to correct that. So, and that works very, very well. It works at low frequency. The next thing we do is we use something, if again, since everybody here I think has a physics background, you know what harmonic oscillators are. Well, we use a harmonic oscillator in the form of a pendulum to suspend the mirror. So that object in the bottom, that sort of colored there, is actually one of those mirrors. It's, in this case, I think it's one of the N test mass mirrors. And it's suspended by glass fibers, which are then suspended to another mirror. That's this mirror or this piece of glass here. And then that happens 2 more times. These are quadruple pendulums. And that actually has a very, very powerful effect on minimizing the amount of perturbations that get transferred to the mirror from the Earth. It's by about a factor of 10 to the 10 or 10 to the 12 over a very narrow range of frequency. And then there are the mirrors themselves. These are actually very, very highly polished mirrors. They're among the best mirrors in the world. And this is what it actually all looks like when you put it together. Now, you don't see any of those components that I showed you before, and the reason you don't see them is because everything is in a vacuum system here. So this is a view into the corner station of the Hanford Observatory. In this case, the laser would be down here, the beam splitter is in here, and these are the 2 arms of the interferometer. But you can see there's a lot of complexity that comes along with this, and just for a sense of scale, again, there's a person for you. So, that's at a very, very sort of high level. This is the detectors that we use to detect gravitational waves. Now, as I started this talk out with, I showed you a detection or a simulation of a binary black hole merger. Well, let me back away from that for a moment and talk a little bit about how we operate these detectors. So concentrate on the top line, the line that says LIGO. We do observing runs. Basically, these detectors, because they're very sensitive, we can't run them all the time. In fact, we're constantly upgrading them. So all of the data and the results I'm going to show you are coming from what we would call our first 3 observing runs, 01, 02, and 03. All right, and we increase, between those runs, we do improvements to make these interferometers more and more sensitive. So back to the first detection, we fondly call this GW 150914. That's the date at which it was detected. The movie you've seen, what I'm showing here on the left is the actual data, and this data is remarkable. And if you look at it carefully, you can actually see how it corresponds to the dynamics of the orbit. So as these black holes are quite far apart, they're orbiting each other slowly, which means the frequency of the gravitational wave is going to be lower, right? As they get closer and closer, and the reason they're getting closer and closer is because they're radiating energy away in the form of gravitational waves. And as that energy leaves, the orbit decays. The energy that's being radiated away is no longer supporting the orbit. The frequency increases. Here, I'm actually going to go back and do that again for you. So the frequency starts to increase as they get closer and closer, and they're spinning close, and the amplitude of the wave gets higher, greater and greater. And so what you map there, the red curve is the data from Hanford, the Hanford detector. The blue curve is the data from the Livingston detector, and you can see that they're not exactly alike because, and we don't expect them to be, because these detectors are noisy. They're not perfectly isolated, but you can see that the waveforms overlap each other quite well. The other thing that you'll note is the strain. So that's the y-axis. So the amplitude of this gravitational wave is 10 to the minus 21. So that's basically a displacement of 10 to the minus 21 over that or 10 to the minus 18 over that 4 kilometer baseline. And it was also a very short event. It only lasted about 0.2 of a second. And that's when that three solar masses was released. So I'm going to show you this data again, but I'm going to show it to you in a different way. And I hope that my sound system is working for you too. So I'm going to now play this back for you. I'm not sure if that came through for you. If it did, what you saw as the data was sweeping and it swept through 3 times the same event, you should have heard a thump. And that thump was basically the sound that the gravitational wave made when it interacted with our interferometer. All right, the gravitational waves that we detect are in the audio band. They're in the band where your ear hears. And in this particular case, these gravitational waves were about 200 to 300 hertz. And you can actually see that here. So this is another way of looking at the data. On the x-axis, again, is time. On the y-axis is frequency. So these are spectrograms. That's the terminology for them. And you can see that as time goes forward, as we go forward in time, the frequency goes up, and that's called a chirp. Right? And that's the characteristic of these coalescing binary systems. As the orbit decays, they spin faster and faster. The frequency of the gravitational wave goes up. They radiate more gravitational waves. I'm going to play it for you again and again. I don't know if you're hearing this. I hope you are. And there, what I've done is I've actually shifted the sound frequency up by about 400 hertz, just so your ear can better hear the chirp. But you can clearly, if my sound was working for you, you could hear that chirp as it was going through. Okay, so why is this important? All right, we've detected a gravitational wave. That's a confirmation of Einstein's theory. It was a tremendously challenging experiment. That is true. But we're interested in actually learning something about the universe, not just detecting gravitational waves. And so this picture here is a nice graphic which sort of shows the impact of gravitational waves, the revolution that we've been living with for the past 5 years of gravitational waves. And on the y-axis, you see the numbers 1, 2, 5, 10, 24. Those represent solar masses. And you see dots. You see we see a lot of yellow dots. You see quite a few purple dots, and you see some orange dots. Don't worry about the orange dots for now. Worry about the yellow and the purple, particularly the purple. So those purple dots represent known black holes in the Milky Way galaxy that were detected from X-ray sources. So we can use X-rays to detect matter falling into the black holes. And as it accelerates, it produces X-rays. And you can sort of, in your brain, count up, there's maybe 25 of those known black holes that were detected through X-ray astronomy. After we did our first observing runs, these are the black holes that we detected in LIGO and Virgo. So one of them was that movie that I showed you. That was, I think that was this one over here. But there are a number of other ones. And in fact, you can see that we actually detect 3 black holes every event, because the 2 black holes that collide eventually merge to form the next black hole. So if you do the count up there, you see that, well, LIGO is doing actually doing pretty good. We've detected about the same number as the X-ray astronomers. It took the X-ray astronomers 40 years to detect those purple dots, the black holes in the purple. It took us 2.5 years to detect the same number of black holes using gravitational waves. And this is only through 2018. So now let me show you the more recent detections. So we've now detected roughly 100 of these black holes. And there's 2 things to say about them that are important. One, the black holes that LIGO detects are much, much further away. They're billions of light years away, not hundreds of light years away or thousands of light years away. And the second thing, and this is where the astrophysics starts to become really interesting, is that you can see that the black holes that we detect are much more massive. They're much heavier, if you will, than the black holes that are seen by X-ray astronomy. So we've detected a whole new population of black hole sources, and that's quite exciting. And I want to focus in on this guy right here. This is one of our most recent detections. We detected it in May of 2019. The reason I want to focus in on it, one, it's a very massive black hole. You can see that the final product, the mass black hole that was produced in the collision, is almost 160 solar masses. It was also the furthest black hole that we've ever seen. So this is GW 190521. We like to put these names on these. We care about our black holes. We like to name them. This is the furthest gravitational wave event that was ever recorded. So this was 7 billion light years away. That in itself is pretty cool. But what's actually even more cool are 2 other things. First of all, one of the black holes that we detected had a mass, the progenitor, the first one of the lighter black holes that were involved in the collision, had a mass of 85 times the mass of the sun. Now that may not mean much until you study astronomy and understand that that's a place where black holes should not exist. The physics of supernova explosions tells you that above about 60 solar masses and below about 130 solar masses, black holes should not be produced in supernova explosions, which is where most of these stellar mass black holes come from. So that's weird. Where did this black hole come from? And one really interesting conjecture is that this might actually be a 2nd generation black hole merger. In other words, the one or both, the 85 solar mass black hole, so now talking to the graphic in the bottom right of the plot, merged with a 66 solar mass black hole. It's quite possible, we can't say definitively yet, but it's quite possible that 85 solar mass black hole was actually produced in the collision of 2 lighter black holes, maybe one that was 40 and one that was 48 or something like that. Same thing true for the 66 solar mass black hole. And so then they got together, they were orbitally bound, and then they formed this. In the end, it ended up being about 142 solar masses, not 145 solar masses. So these could be basically seeds of new and bigger black holes, and that's quite exciting. There's a lot of other interesting physics that comes out of this, including the nature of the way the black holes were spinning relative to their orbital axis. This tells you something about maybe where they formed. Did they form in the center of a galaxy? Did they form in a globular cluster? There are hints that suggest that they formed in sort of very dense stellar environments, and that's very exciting also. Finally, this is the most massive black hole that was ever detected by a gravitational wave detector, and it's the first intermediate mass black hole. Now, there are supermassive black holes in the center of most galaxies, including one in our galaxy. And one of the questions that's being asked is, how did that supermassive black hole form? Maybe it was formed through subsequent mergers of lighter mass black holes. So we don't know the answer to that yet, but that's one of the questions that is very, very interesting and that gravitational waves could actually tell us. So now let me move on to the other great detections that have been made, in particular 2 of them over the past 5 years, and those are binary neutron stars. So I want to start this by basically coming back to something that I talked about earlier, which is, I said we study the universe using telescopes, optical telescopes or X-ray telescopes. Well, what we do in something called multi-messenger astronomy, gravitational wave multi-messenger astronomy, is we study the universe using optical telescopes, X-ray telescopes, and gravitational waves. So we use different kinds of observing modalities, methods, to actually discover new physics. So the idea is this picture right here. So if you have a binary neutron star merger, and I want to spend a little bit of time talking about neutron stars here, they have matter in them. So a neutron star is produced in the explosion, the supernova explosion of a sun that could be made, or a star that could be maybe 10 solar masses, maybe 8 solar masses. If the star is heavier, more massive, when it explodes, it could produce a black hole, like some of the black holes that we showed you, that I showed you earlier. But for lighter stars, when they explode, when their core collapses, it collapses into something known as a neutron star. And these are really exotic objects. They are about 1.5, 1.4, 1.5 times the mass of the sun. All right. When they're produced, they're made up of pure nuclear matter. So you can think of them as basically being in a giant atomic nucleus, mostly made up of neutrons, but that's 25 kilometers in radius. So they're incredibly dense. In fact, they're the most dense matter that we know in the universe. If you were to take a teaspoon of a neutron star, it would weigh about 1 billion tons if you were to weigh it on Earth. So because it's just pure nuclear matter. Because they're made of matter, when they collide, when they do this, and I'll show you a simulation in a moment, but when they orbitally decay and collide with one another, they not only produce gravitational waves the same way the black holes do, but they produce light across the electromagnetic spectrum. They may produce neutrinos, although we haven't actually detected any of that yet. So the idea here is that if you can catch a binary neutron star merging, all right, and look at it with gravitational waves and look at it with all these other modalities, visible telescopes, radio telescopes, X-ray telescopes in space, you can actually learn a lot more about the event. And in fact, the first gravitational wave that we detected turned out being that kind of event. So, but there's a challenge, and I have to tell you what the challenge is. The challenge is that if you think about a telescope, you can point a telescope in space. So you can go out at night, you look up, you see a star or a planet, and you get your telescope out and you point it, and you have a very good idea of where that object is in space. Gravitational wave detectors are fundamentally different than that. In fact, you could think of them more as microphones rather than telescopes. So this is actually very much analogous with the fact that gravitational wave signals produce sounds we can hear. So they're more producing sounds than light, and they're harder to locate. In fact, one gravitational wave observatory is pretty much insensitive to the sky location. So if you want to detect, if you want to be able to identify where a gravitational wave source came, and if we can do that and do that quickly, then we can tell our friends who operate telescopes, please point your telescopes in this direction, and they can actually capture the light that's emitted from the event. So the way we do that is we use something called triangulation. Since we can measure the phase of the gravitational wave very easily, what we can do is basically, by knowing when the gravitational wave hit different detectors on the Earth, and in this case, there are the 2 LIGO detectors, which I showed you before. We also work in close partnership with a third gravitational wave detector in Italy called Virgo, right, very near the town of Pisa. All right, by measuring the time of arrival of the gravitational wave signal, that gives us better information. It's still not anywhere near as good as a telescope can do, but better information about where a source came from. And so if we can do that quickly, all right, we can actually detect, we can do multi-messenger astronomy. All right, so right now we actually operate 5 gravitational wave observatories, the 2 in the US that I told you about, the 1 in Italy that I just showed you, Virgo, another detector in Germany, and very recently a new detector that came online in India. There's another detector that's being built. I'm sorry, detector came online in Japan, and then there's another detector that's being built in India. And the reason all these gravitational wave detectors are in operation or becoming in operation is because this field is really very much a new and exciting field. So a lot of countries want to get involved with it. So all right, so I'm going to start this with the movie. These are a simulation of 2 neutron stars spiraling around one another, black hole. When they collide, they produce this burst of energy that comes out perpendicular to the orbit, and that energy contains gamma rays, it contains matter, it contains light. There's emissions across the electromagnetic spectrum. And we were fortunate that on August 17th, I didn't put the name of the event here, this one is GW 170817, we were fortunate enough to see a gravitational wave signal in our detector, and that's shown in the bottom right-hand plot here. Again, this is the spectrogram, so there's the time along the x-axis and the frequency along the y-axis. And as you can see, what happens, as I told you before, these objects, as they spin around one another, they spin faster and faster and eventually merge. All right. At the same time and independently, and this is actually an important part of the story, independently of LIGO and Virgo, X-ray telescopes, gamma ray telescopes, in this case the Fermi telescope run in the United States and the Integral telescope run from Europe, detected a burst of gamma rays approximately 1.7 seconds. So the time difference between these two, when the gravitational wave signal ended and when this was detected, 1.7 seconds. And with that information, with the information that you get from LIGO and Virgo, you can ask yourself, and we were able to do this in about 3 hours, you can ask yourself, how accurately can I locate that event? And it turns out with all that information, you can see the different colors here show the information that you get from either the X-ray or the gamma ray satellites just from LIGO alone or from LIGO and Virgo. And that little banana, the light green banana there, is what we call the error box. And that's actually not so big, even though it's a lot. You could fit 3,000 moons in there, but that's not. The astronomers know how to deal with that. They can actually look over that range, and so they did. And so we sent out an alert saying that we saw a signal in that part of the sky. This is sort of projecting outward. All right, and the astronomers who operate fast telescopes, robotic telescopes, actually went to that part of the sky and zoomed in. And here's what happened. So they zoom in and they look for galaxies. We know roughly the event is about 140 million light years away. They look for galaxies and they zoom in and they find this one galaxy. All right, that's about 140 million light years away. This galaxy is NGC 4993. And if you look at that picture there, you'll see, there's stars in the foreground, but the haze that you see is actually the stars from the galaxy that you're looking at. And then in the center, you see a brighter spot, which is the galactic bulge, the center of that galaxy. But when the astronomers looked at it, they saw this. They saw that extra thing there. That extra thing is circled in red. And that is the remnant of those 2 neutron stars. That's called a kilonova. And this was the first time that astronomers had detected a kilonova that was produced immediately after the collision of 2 neutron stars. And this was a remarkable event. And I could spend a whole talk just talking about this event, but I want to say 2 things about it. First, what did we learn? we learned something about how elements are formed. So this is a periodic table. I think everybody is familiar with the periodic table. You recognize hydrogen, helium, there's gold here. Where's gold? Gold is down here. There's silver. And if you look, there's color coding, and I'm not going to spend a whole lot of time talking about the differences in color coding, but what the color codes show you is the physical processes that produce nuclear elements. So where does hydrogen come from? Hydrogen came from the birth of the universe, the Big Bang. Helium, for the most part, came from the Big Bang. The elements in blue mostly come from supernovas or from exploding white dwarfs. The elements in yellow, the heavier elements, all right, anything that's in yellow is produced by a emerging neutron star. And this is something that had been speculated upon for many, many, many years. It's called nucleosynthesis, in particular heavy element nucleosynthesis. But in order to verify that, the astronomers had to take spectra of that kilonova. And what that spectra showed was that it verified the theory that these heavy elements, such as gold, such as silver, such as platinum, such as uranium, are very likely and mostly produced in the collision of a binary neutron star. So if you're wearing some gold jewelry, I have a gold ring on my finger, my wedding band, this was probably produced billions of years ago in the collision of these two neutron stars. So that's actually a pretty remarkable result. Let me give you another remarkable result here. The fact that we were able to see the gravitational wave, so this is the same data I showed you before, the fact that we were able to see the gravitational wave and the X-rays, and because we timed things very carefully, we were able to measure the time difference, and that time difference is about 1.7 seconds. All right, so the gravitational wave signal arrived on the Earth about 1.7 seconds before the gamma ray signal. Now, the simulation that I showed you, you saw the gravitational wave being produced, at least in your brain you can see that for yourself. And at the point of collision, the gamma rays are produced. All right. In fact, the gamma rays are probably produced at the point of collision. So the time difference here is about 1.7 seconds. The object, we know it's actually about 40 million kilometers away, but conservatively was 40 megaparsecs away. That's about 140 million light years. We're conservative. We said it's about 100 million light years away. So that's that D there. You can actually use the time of arrival and ask yourself, if we know that delta T, right, the time difference, we can calculate the difference between the speed of gravity. So that's V GW in that equation in the upper left, and C, which is the speed of light. All right, and the calculation is quite simple. All right, if delta T were 0, all right, the time difference would be the difference between would be 0. And in fact, to uncertainty, when you actually unfold the uncertainty and do the uncertainty analysis, you actually show that the speed of gravity, and that's in the second equation, is 0. Is the speed of light. The speed of light and the speed of gravity are the same to about 1 part in 10 to the 15, which is a remarkable result. So this is the first time that well, it's not the first time that we've been able to measure the speed of gravity, but it's absolutely the best measurement. And it actually puts a limit on the mass of the graviton, the mass of particles that carry the gravitational wave field. So this is another really remarkable result. All right. More recently, we've been able to see a really interesting object that no one understands. And this highlights another aspect of the revolution, that when you have these new instruments and you're probing new regions that you hadn't been able to probe before, you see new things that you don't understand. And in this case, we were able to see an event that lives in a place, again, where it shouldn't. One of the objects colliding was 2.6 times the mass of the sun. All right. We've never seen neutron stars that heavy. We've never seen black holes that light. So this object, we don't know really what it is. It's either the heaviest neutron star ever detected. And if it is, that's interesting because it's heavier than predictions would allow neutron stars to live. In other words, the upper limit on their mass is less than that. Or it's the lightest black hole that's ever been produced. And that's interesting too, because lighter black holes, quite frankly, it's hard to see how they form unless maybe they came from the primordial universe, the Big Bang itself. So there's this discovery is something that we don't completely understand yet. But what we do know very well is that this was an object that had a mass that has not been seen before by other objects, and so that's actually pretty exciting. I'm actually going to conclude here. Yeah, I think I'm running on time, and talk about the future and just say in very broad strokes what the future of this field looks like. So everything I've talked about today, I've talked about LIGO and ground-based gravitational wave detectors, and the periods of those waves are measured in milliseconds. All right, the frequencies are hundreds of hertz, as I said. They're sent to your ear. But gravitational waves exist across a spectrum, just like electromagnetic waves exist across a spectrum. So you can have gravitational waves that have longer wavelengths from minutes to hours. They are produced, for example, by the collisions of intermediate mass black holes. You can detect those if you have the right detector. And there's a project going on right now called LISA, Laser Interferometer Space Antenna, to build a massive gravitational wave detector using 3 satellites, you can see in the picture, separated by about 2.5 million kilometers in space. Right? LISA, we hope, will launch in the next decade. You can even think longer wavelength. There are gravitational waves that have periods of years to decades. These are produced by the collision of supermassive black holes that exist in the center of galaxies. So in some sense, collisions of galaxies themselves. And actively using radio telescopes, scientists are looking for these events right now. At the very, very far low frequency, long wavelength end of the spectrum, you can have gravitational waves that have wavelengths that are on the order of the size of the universe, periods of billions of years. And they are produced by the Big Bang. And there's a project going on right now to detect those gravitational waves in a completely different way than we go forward here. So let me conclude by quoting Sir Peter Medawar, who is a Nobel Prize-winning biologist in Britain. He said something that I think is very appropriate. He said, "Observation is the generative act in scientific discovery. For all its aberrations, the evidence of the senses is essentially to be relied upon, provided we observe nature as a child does, without prejudice or preconceptions, but with that clear and candid vision which adults lose and scientists must strive to regain." I think that's very touching because it tells us, what we see, we have to understand the way a child does. So I'll conclude my talk right there, but I do want to acknowledge everybody who participated. So this is the group of scientists and engineers at the LIGO laboratory, both at Caltech, where I am, also at the 2 observatories, and at the Massachusetts Institute of Technology. And finally, all the results that I presented to you today were produced by the LIGO Scientific Collaboration, which is a group of 1,000, actually about 1,400 people across the world, from many countries in the world. So I'm going to stop there. I hope I've conveyed the excitement of the revolution to you, and I will be happy to take any questions. Thank you.
Yeah, thank you very much. I think I speak for everyone when I say that you clearly transmitted to every one of us how amazing this discovery was and how a big technological achievement it was. So the first question is, what is the status of the Kagra Observatory? When is it joining the collaboration? Is it shutting down nowadays because of the pandemic? Is it already observing? If it is, why anything has been put to the public about them?
Right. So the Kagra detector actually did a short run in early 2020. I think they ran for 3 or 4 weeks, maybe a little bit longer, in 2020. And they're actually shut down right now. They did have some impacts from the pandemic, as we did. But they are actually, their detector is in what we would call the early stages of commissioning. So the Cogro detector is not nearly as sensitive as the LIGO detectors or the Virgo detectors. So right now, the Cogro detector is working on improving its sensitivity, and actually as are the LIGO and Virgo detectors. And we all hope to come back online probably in the middle of 2022 and start our next run, which would be the O4 observing run. So no, Cogro is very much a working detector now.
Excellent. Thank you for your answer. Another question we have is that you mentioned in your presentation that it is not good to be so close enough to the source to detect gravitational waves, but due to the dissipation of energy, is there like a sweet spot where detection would be ideal?
If I understood the question, you said it's not good to be close to the source. Is that right?
Yeah, I think from your presentation you mentioned that it would not be good to be close to the source.
Well, actually, the closer you are to the source for gravitational waves, the better, because the signal, and I don't think I did talk about this, but the signal falls off as 1 over the distance. So if you have a source of gravitational waves and it radiates, the amplitude of the gravitational wave, if you go a distance d away, will fall off by 1 over d. Whereas if you think about light, for example, that falls off as 1 over d squared away. So, so in fact, being close to the source, it depends a little bit on what kind of source. So for supernovas, for example, and I only talked a little bit about supernovas, the gravitational wave emissions from a supernova explosion are predicted to be very, very tiny. For black holes, solar masses of energy are converted into gravitational waves. In supernovas, it's 10 to the minus 8 or 10 to the minus 9 solar masses. So much, much less energetic. There you want to be closer. So we couldn't, for example, we couldn't detect a gravitational wave from a supernova outside our galaxy. For other sources, closer is indeed still better, because the amplitude of the signal will be bigger. The signal to, what you're interested in the detection is what's the signal to noise. All right. And we like to have signal to noises of 10, 20, 30, signal to noise of 100. The bigger the signal to noise, the more accurately you can map out the waveform. And the more accurately you can map out the waveform, the more accurately you can extract the parameters of the source, the masses of the source, the spins of the source, things like that. If you're too close, let me just take the question to its ultimate limit. If you're as close as as we were to that movie, I would be worried that you might actually get sucked into the black hole. So that would actually be a bad thing. Okay, but other than that, I think, yeah, if there were, and you don't want it. The other source, I guess, would be a binary neutron star merger. If you happen to be unfortunately aligned along the axis where the gamma ray is emitted, that would be problematic for you too. That would be an end of life event for us. But fortunately, that hasn't happened yet. So.
Thank you. So another question is, I read once that we use 2D grid to represent the space-time, as it is easier to show it that way. Is that true? In case it is true, how will gravitational waves will be shown in a realistic 3D space-time grid representation? In the movie, we see that the 2D grid representation, they move up and down in 3 dimensions.
Right,
Would
right.
Gravitational waves move on higher dimensions?
That's correct. The problem with visualization is that space-time is actually 4-dimensional when you include the time dimension. The time dimension is encoded in the dynamics of the gravitational wave. So when we show cartoons, and that first movie that I showed was in fact a cartoon, it only shows the fact that there's two space-time dimensions rather than 3 space-time dimensions there. So visualizing gravitational waves is a little hard. There actually are better, the visualization was a visualization that was made at Caltech in my group. There are other visualizations that are maybe better, but it's hard to have a 3D visualization when you only have 2D screens. You know, that's just the nature of, you know, geometry.
Yeah. Okay. We have another question about the detectors. How come the detectors inside the arms of the LIGO can tell if a gravitational wave has passed through Earth? If when a gravitational wave transfers the Earth, all the space inside the arms, the whole laser beams, mirror cables, instruments, is displaced equally.
Right,
We
right.
Yeah, so that's the
Okay, all right. Yeah, that's a good question. It's a question that gets asked a lot by people who, you know, when you hear what gravitational waves are, you and think about it carefully. It's a you know, a very smart and natural question to ask. And the answer is simply that you know, everything that sits in space is being affected by the gravitational waves it passes. So the wavelengths of light are actually stretched a little bit in one. But, and this is the key, what we're measuring, there's a couple of ways to think about this. One way to think about it is what are we actually measuring? What we're measuring is the time that it takes for a photon, for two photons. One that goes down the Y-arm, so leaves the beam splitter, goes down the Y-arm. The other photon leaves, you know, goes through the beam splitter and goes to the X-arm and comes back. And what the gravitational wave does, and you can write down the equations of general relativity very simply. It's actually a little bit of calculus, but not too much. And what you can see is as a gravitational wave passes, what it does is it basically elongates the space in one direction, say the Y direction, and shrinks the space in the X direction, such that the photon that travels down the Y-arm takes a little bit longer to get back, and the photon that travels down the X-arm takes less time to get back, integrated over the gravitational wave signal. And that manifests itself as a phase shift of one relative to the other, even though the light has changed wavelengths. And in fact, that's the other way you can think about this. There's a famous experiment in physics called the Pound-Rebka experiment, which was the measurement of the redshift of a photon. It was done in a laboratory. It's remarkable. It's a tour de force experiment. But what that experiment showed was that as a photon leaves a gravitational wave field, it redshifts, because basically the gravitational wave field itself, all right, redshifts the photons through the fact that the curvature is different, all right? And that's in fact what's happening in our interferometers. The other way to say what I just said was to say the following, that one photon, the one that goes down the X-arm, which gets longer, and remember, this is all dynamic. As the photons are traveling, the gravitational wave is stretching at the same time. What happens is you can think of it as going into a different gravity. It's feeling a different gravitational wave field, a gravitational field, than what you get on the X-arm. So the one that travels down the longer arm, the stretched arm, in my case it was the Y-arm, gets redshifted. The photon that travels down the X-arm, because it's a little bit shorter relative to what it was, it gets blue shifted. And so when they come back together, they're actually different color photons. And that's exactly what you'd expect from Einstein and from what a gravitational wave signal does. So the key is not to think about this as we're measuring wavelengths, even though we show the interferometry that way. We're thinking about, what we're measuring is the time of arrival, the time of flight of two different light waves that travel down two different arms. And that is absolutely and definitively tells you that you will get a signal from a gravitational wave. That was a little bit complicated. I hope I got the point across.
Yeah, and it was a really good insight for those that want to think deeper about how we detect gravitational waves. Another question, what sort of phenomena should we be able to observe in an interferometer in space, such as the planned LISA interferometer? How close could we look at the Big Bang?
So the LISA interferometer is sort of you can think about it, the last slide that I showed, which had the gravitational wave periods, you can roughly think about the gravitational wave period corresponding to the mass of the object that you're looking at. So in our case, the ground-based gravitational wave detectors, we look at relatively low mass objects, and I mean in an astrophysical sense. So we're looking at objects that have stellar masses. Those two black holes that the first black holes were about 30 solar masses. These black holes on the slide that I'm projecting now are, on the order of 100 solar masses. The supernovas that we look for would be, a few solar masses, 5 solar masses. Neutron stars are even less. As you get to longer wavelengths, which is what the space-based interferometers are going to look for, you're looking at heavier objects. You're looking the signals that are produced by more massive objects, and they're naturally lower frequency signals. So there you would see intermediate mass black holes, maybe 10 to the 4 to 10 to the 6 solar masses. And by the way, we don't even know if those sources exist. Another source that you would see, which is a little bit different from what I just said, but it has to do with the dynamics of the object, are white dwarfs. So if you think about stellar life cycles, what happens when a star is born, it goes through its life cycle, burns nuclear fuel. Depending on how massive the star is determines where it ends up. If it's really, really massive, it becomes a black hole. If it's a little less massive, and again, I'm being very qualitative here, but I hope I'm getting the point across, it becomes a neutron star upon supernova. If it's not so massive at all, like our sun, which is a pretty light mass star, it actually doesn't even explode. It just sort of burns itself out and becomes a white dwarf and then a brown dwarf. And there's lots of stars in our galaxy, and actually in the universe, that are in binary systems that are paired around one another. And so LISA, the space-based interferometer, those signals are produced by the orbits of white dwarfs, and they're produced over longer time periods. So you can look at white dwarfs. The problem with white dwarfs is they shred. They basically, when they get too close to one another, they just sort of, the gravitational wave attraction between them just rips them up. So they don't emit in our band. The other thing you can look for with LISA, and this is another way of thinking about multi-messenger astronomy, is they will actually see the gravitational wave from the black holes that LIGO and Virgo see years before we see them. So because they're looking at much lower frequencies, when the orbits are much slower, the objects are much further apart from one another. So they'll be looking at a different sort of time in the evolution of the black hole. So sort of summarizing, LISA is going to be tuned more towards lower frequencies, which is heavier masses, but it can also see some interesting lighter mass sources that are either LIGO can't see or can't look at a given time. So,
thank you. So, what advice would you give us as engineering physics students if we would like to focus on something like LIGO?
Great. So the reason LIGO works so well is because we have a lot of engineers. The scientists, I myself am a physicist, we come up with crazy ideas. And then we try and make them work. And because we're physicists, we're good at thinking about the physics of something, but maybe we're not as good as engineers as thinking about how do you actually make something work. And so if you look at the different subsystems, the different parts of the interferometer, let me show you. Let me see if I can find it here. Yeah, this is a great example. All right, so that picture that I'm showing you there is a tour de force in optical engineering and a tour de force in mechanical engineering. So that structure is designed to hold by wires and by fibers those mirrors. The mirror at the bottom is the one that's actually seeing the laser light. We had to make 8 of those, and they had to all be identical. And the way we did that was We have extremely talented mechanical engineers who design them. We have extremely talented electrical engineers who do put the electronics in for them. We have extremely talented controls engineers. One thing I didn't talk about was that the interferometer is basically a bunch of large feedback control loops, and designing quiet control loops, designing stable structures, designing systems that can suspend. The mass at the bottom is 40 kilograms by a piece of glass, a fiber that is 100 microns or a few hundred microns in diameter. That takes a huge amount of design work, a huge amount of testing, a huge amount of engineering. So most of what we do in LIGO is engineering. So I think there's lots of opportunities for engineers, not just in LIGO. I mean, if you think about big telescopes, the engineering that goes into making a 30-meter or 40-meter aperture telescope, that's a huge amount of work there. So yeah, the advice I would give you is keep studying engineering, look for opportunities to work for big cool science projects like this, and join us and help us make our instruments work.
Thank you. Now, the following question is a little bit more specialized. So when light passes through the system of beam splitters and mirrors for some lasers, the feedback effect causes chaotic dynamics. How can you deal with this undesired laser dynamics?
Yeah, so we don't really see that so much. And the reason we don't is because it comes back to what I was saying before. First of all, our lasers are extraordinarily stable. So, and we actually have many different control loops to stabilize them. So our lasers are stabilized in frequency. So they're extreme. We talk about lasers, we say that lasers are very monochromatic. In fact, lasers are not so monochromatic when you're trying to detect gravitational waves. Remember, I said we need to split a fringe that delta phi of 10 to the minus 12. So the way we do that is we frequency stabilize the laser, which means we have to measure the frequency of the laser in the interferometer, and then we have to feed back to the laser to keep the frequency at the control point. All right. We also do that. So we do that with the amplitude, or the power of the laser is also sensed and fed back. And that's the role of some of these filter cavities right here. If you look at this, my cursor, there's that triangular optical cavity. So light comes in, goes around, it goes around there about 500 times, and then goes out this way. That cavity, because of its characteristics, is actually a very stable source, both for frequency and for reference and for amplitude. I'd also the other third thing we stabilize is the mode structure of the light. So the way we get around, what I would call classical chaotic dynamics is by having feedback loops that constantly sense, the status of the laser in frequency and amplitude and pointing, we would call it, and just knock it out by a feedback loop. Having said that, there actually is a place where we do get into a realm of uncontrolled dynamics, and it's a problem for us. And it has to do. I'll try and do this very quickly because I know it's late in the day there. The mirrors themselves are, because I said they're suspended by fibers, so they're not rigidly held. So that means the mirror. See if I can do it here. So you have a mirror. The mirror is free to move around. It can swing in all different directions. It can move backwards and forwards. In fact, that's the gravitational wave signal comes from that kind of motion. It can move in yaw. It can move in pitch. A mirror can do this or this. All right. When the laser beam hits the mirror, if it hits off center, as it always does, all right, it can actually push the photons have pressure. They have radiation pressure because photons carry momentum, and it can introduce torque. And that couples the photons to the mechanical modes of the suspension, optomechanical coupling. And that can lead to all sorts of problems. And in fact, it can even couple to the modes of the mirror themselves. The photons can actually drive thermal modes, acoustic modes in the mirrors themselves. And those kinds of things are problematic, and they become much more problematic when you go to higher laser powers. And we have many ways to control them. It would take another 15 minutes to go through all of it, so I won't say it. So the kinds of things we worry about are not so much the classical chaotic dynamics that you see with regular lasers. We just feedback that out of the system, but are these dynamics that have to do with the fact that we have suspended mirrors and very high power lasers.
So if it's all right with you, we are going to ask a couple more questions. So and the talk for today. So for these kind of precision experiments, is the shape of the beam in a specific shape of, for example, any Gaussian beam with any alteration?
Yeah, so that's another great question. Yeah, so the laser beam is exquisitely Gaussian. At least we try and keep it as zero, what you would call in Gaussian optics a pure TEM, transverse electromagnetic TM00 mode. So a pure Gaussian mode that you would get. And in fact, some of those filter cavities are actually very good at knocking out some of the higher order, the TEM 10 or 01 modes like that. In fact, the mirrors themselves, and this is a little bit of fun optical engineering, the mirrors themselves are not perfectly spherical. Even though we want them to be. In fact, their polish is exquisite, but it's not perfect. And so the shape of the mirror itself actually can introduce higher order modes when the beam bounces off of it. So we sometimes see evidence, for example, of 7th order modes, TEM 3.4 or TEM 6.1 or something like that. But they're very low power. Ultimately, and we don't like those modes because they can interfere with the main mode and introduce noise into the interferometer. So we go to a lot of different ways of knocking them out. If you know something about optics, you know that if you have a Gaussian mode, if you go to higher order modes, the size, what we would call the mode volume, the size of the mode goes as the square root of M plus N, where M and N are the indices of the TEM 00 or 01 or whatever. So the modes get bigger the mode sizes get bigger as you get to higher order mode structures. And we actually put in baffles and apertures and things like that so that we suppress those modes. But yeah, you do have to worry a lot about that actually. So, and it's a lot of optical engineering.
Excellent. And what were or are some of the unforeseen challenges faced in a collaboration project such as LIGO?
That's a great question because there are so many different ways to answer that. I'll answer it two different ways. One is technical. All right, so these interferometers are very complicated, and when you first start putting them together, we didn't anticipate many of the challenges that we would have building them. And I will go back to maybe almost 20 years ago when we were building the first generation of these interferometers. Let's see if I can, here's a nice picture. The Livingston interferometer happens to sit in a forest. You can see all those trees. And that forest is actually actively farmed by a company that basically cuts down the trees and produces, lumber products from them. As you can imagine, cutting down a tree is a very noisy thing. It produces a lot of ground motion, and that took us by surprise. And it took a year or two to actually develop a seismic isolation system that was capable of even just keeping the interferometer operating, not even making it sensitive, just keeping the interferometer locked. So that's one of many examples that I could give you technically. But I'm going to answer the question in a different way. Actually, I think one of the biggest challenges in these big projects is the fact that you've got a lot of people, and those people are all over the world, and those people come from different institutions. And so first of all, you have to have effective channels of communication. You have to have effective ways of mediating differences. Some people might want to do this or do this thing. Some people might want to do that. So you have to have ways of making sure that everybody stays focused and keeps the project going in the direction that it's supposed to go in. I mean, one of the challenges we have now with the pandemic is the two LIGO sites and Caltech and MIT. We used to travel regularly to the sites because there's expertise that was needed at one site or another observatory or something like that. We can't do that anymore, and so that's a challenge, is keeping communications up. So, but there are many challenges, but in the end, because we all want to detect gravitational waves, we work them out. So,
excellent. So now for the final question of the evening. I would like to allow one of our professors from our university to ask you directly the question. So, Professor Raúl, do you care to ask?
Sure. I just apologize if my dog starts barking. So the question is, how do you take care of the deformation of the mirrors due to its own weight? Because you have very heavyweight mirrors there, and they deform under its own weight. So how do you take care of that?
It does deform a little bit. So we actually measure when we get the mirrors. Let me walk you through the process. So the mirrors are 40 kilograms. Dimensionally, I think they're roughly 38 centimeters in diameter. I think 18 or 20 centimeters thick. I think it's 20. And they're made of fused silica. We polish them to make them as spherical as possible, and then we have to measure them. And so when we measure them, we measure them in a Fizeau interferometer that can measure the radius of curvature along the two different directions. And it turns out that the sag, the differential radius of curvature from in the direction of down gravity versus side to side, is about, if I remember correctly, 1 part in 10 to the 6th or something like that. And that, when you model that and you say, okay, what effect does that have on the modes of the cavity, arm cavities, turns out not to have a big effect. The bigger effect, excuse me, that we have is that the mirrors are coated. So the end mirror, the one in the end, is actually a very high reflector. It's 5 nines, 9.9999, I think 10 ppm, 10 parts per million get out. The input mirror is actually transmissive. I think it's about 1.5% transmissive. But the coatings themselves are absorptive. So because there's huge amounts of power in the arms, right now we have about 200 kilowatts in the arms, about a watt of power is absorbed, maybe a little less than that, half a watt to a watt, is absorbed in the coatings, and that actually deforms the mirrors. So the way we deal with that is we actually have what we call them thermal compensation systems. So we actually put heat, so that the deformation by the laser beam puts a bump sort of in the center of the mirror, and actually the bigger effect is that it actually puts an index, changes the index of refraction of the substrate as the beam travels through, because the input test mass, there's that 20 centimeters of glass that the beam travels through. So the coating heats up, and the light and the heat diffuses into the substrate. And so the way we deal with that is we have basically a ring heater. Basically, you can think about it as a toaster coil that is sits on the outside of the mirror. I'm not sure if you can see it here. No, you really can't see it in that picture right there. But that actually deposits heat into the edges of the mirror to compensate for the heating in the center. So that's the way we deal with that. But the sagitta differential is not big enough to worry about. We are thinking about, and I didn't have time to talk about this, we are thinking about what comes next. And what comes next is probably going to be a much bigger interferometer. Instead of 4 kilometers, maybe 20 or 40 kilometers, with bigger test masses. That the more massive the test mass, the more sensitive in principle you can make your interferometer. And there it might become an issue. So we have to think about it a little bit more. That was very long, but I hope it answered the question.
Yeah, sure. Thank you.
So now, just to end, we'd like to transmit to you a message that one of the person from the audience sent, and they say, "You are such an inspiration. You, doctor, is the reason why I'm studying physics. I dream to be a great scientist as you."
I'm touched. Thank you. That was it's a very, very kind thing to say. I wish you the best of luck in your career in physics. Thank you so much for the opportunity to speak to you.
Thank you for coming to our symposium. We are very grateful that you gave us some time from your busy schedule to give us this talk.
It was my pleasure.
So now, with this, we conclude the events from today. We'd like to remind everyone that any further information or doubts, you can ask us through our Instagram account. And once again, we'd like to thank our sponsors, Isolenum and Skills for Industry. So, and with this, we conclude the events for the evening. Thank you.
Okay, thank you. Bye-bye.